Okay, so here we have today our last talk of this year, and hope to see you back in the next year. And our today's speaker would be Yasir Iqbal, one of our colleagues from IIT Madras, who is one of the very well-known researchers in the field of quantum spin liquids, and he would be giving us a colloquy on a hybrid of a colloquium and a seminar on this topic today. So over to you, Yasir. We are very thanks for agreeing to talk.
No, yeah, thank you so much, Ian, for sort of inviting me. And I'm sorry I had to give this in November, but I was sort of a bit burnt out, I felt. So I needed time to, sort of give a nice colloquium. So I asked him to replace me, and he was kind enough at a short notice to do that. So yeah, okay. So yeah, so let me begin. So I'm going to talk about it's going to be sort of a colloquium, also a bit technical at some points, but also very lucid at others, in which I'm going to talk about quantum spin liquids, right? And which have come to define what essentially is one of the prototypical systems where many of the ideas defining modern condensed matter physics have arisen. And there's a sort of catchy subtitle. I mean, a search for fractionalization and gauge fields in quantum matter. I hope I'm able to, explain to it both in a lucid and a technical way. So the outline of the talk is going to be like this. I'll first sort of start from the 30s when people were still thinking about how do you distinguish different phases of matter? When do you actually call two different states of phases of matter is actually different, And what then arose was actually the idea between relation between internal patterns and structures and orders and broken symmetries, which was termed, has been called the Landau paradigm, which essentially governed our understanding of all phases of matter, we thought, till the early 80s when the shock came. And I'm going to describe to you what that shock was. And it showed us that there's a world beyond where you cannot relate orders and broken symmetries. Then I'm going to come to actually describe to you and explain the whole historical evolution as well as the current state of the field of quantum spin liquids, which are, as I said, one of the very hotly studied candidate material systems as well as theoretical model systems where this Landau paradigm really falls on its face, both in terms of symmetry breaking theory as well as the Fermi liquid theory. And the systems in which they are supposed to be found or have been claimed to be found, which are called frustrated magnets. Then I'm going to get a bit technical, where I'm going to describe to you the ideas of fractionalization, which is thought to be the smoking gun signature of a quantum spin liquid, and the associated projective symmetry groups, which is a mathematical framework which is used to describe orders which do not feature any broken symmetries. Then towards the end of the talk, I'll try to spend some time on defining to you and presenting, an exotic class of spin liquids, which are called algebraic spin liquids, which when I started my PhD on, it was a topic in 2009-10. Actually, it was, being ridiculed. I mean, if you worked on algebraic spin liquids, but now with a lot of work on understanding, QED3, the stability of QED3 Lagrangian in the presence of relevant monopole perturbations, it's come to be that it's not totally purely a product of our imagination, that algebraic spin liquids can actually exist as stable phases of matter in spin systems. And the U1 Dirac spin liquid, which is the most famous among this class, has been now claimed to be found in a lot of studies, numerical studies of frustrated magnetic systems. And then I'm going to wind up with this. So let's see how it goes. So, okay, so the story begins long time back in the 30s, so when people were still grappling with the, how do you, if I bring to you two substances, how can you actually say that they are actually are in a different state? So the great Landau actually then brought the idea that all states of matter, or all phases of matter rather, can be distinguished by looking at their internal structures, or internal patterns, or internal orders, howsoever you may want to call it, right? And when you say that two phases of matter are really different, then they must possess different internal structures, okay? By this argument, it was very clear that there would be in principle no difference between a liquid and a gas, because both are actually homogeneous and isotropic. And it's difficult to imagine that a gas surrounding us, like the air that we breathe, has some kind of an internal structure. It's a very weakly correlated system. Then as you crank up pressure, I mean, you enter into some kind of a liquid state. The liquid is more correlated, but still pretty disordered, right? And I don't see, if you do deep sea diving, and you look around in a deep ocean, you will start seeing, even if you had very good eyes, some internal structures in deep sea. Every direction would look the same. Even if you swam a few kilometers, few meters, things would still look the same. It's homogeneous and isotropic. And this is reflected in the fact that when we study the pressure temperature plane of the phase diagram, right, the line that separates the liquid and the gas terminates at a certain point here. Right? This basically tells you that if you did an experiment and you took vapor and you started increasing the pressure, right, and as the pressure, went up, you start getting more and more misty, and it'll become whitish, cloudy. And at some point, it'll become a liquid. But at no point can you tell that the gas has stopped existing and the liquid has started, right? Or vice versa. Well, this is not the case on the other line. The other line goes on to infinity between the solid and the liquid, telling you that there is a fundamental difference between a solid and a liquid. And we all know what that is. That is, solids, by which I mean crystalline solids, have a certain beautiful, like snowflakes or something, have a beautiful internal structure to them, right? When you look at a crystalline solid inside, not all directions look the same. There are certain directions in which you find atoms. There are certain directions in which you find atoms after a much larger distance. So what happens is that um, uh, the so the thing is that according to this understanding of phases of matter, a solid is very different from a liquid or a gas, whereas a liquid or gas are the same. They only differ quantitatively in one number. That's called the density, right? That's all there is. Now, there's a second insight that was made by Landau, and that was basically that not just all phases of matter are distinguished by their internal structures, but that these structures can be ascribed to certain symmetries, or more technically to be correct, broken symmetries. So this connection is this is the key connection that formed the basis of his two works that appeared in 1937, that whenever you have certain orders, patterns, or structures, you can always ascribe them to certain broken symmetries. So let me be less technical. What do I mean? If you look at a gas or a liquid, right, and I told you it's homogeneous and isotropic, right? So the thing is that it has a continuous translational symmetry. It has a continuous rotational symmetry, right? Now, when you cool down that substance and it solidifies, that continuous translational symmetry is broken to a discrete translational symmetry. Okay, that's broken to a discrete, and the continuous rotational symmetry is also broken down to a discrete rotational symmetry. This in crystals is called the point group symmetry. Right now, this relation between patterns and broken symmetries was actually the backbone of our understanding of all phases of matter, we thought. And it was so successful that it was almost impossible to think of any system which could escape this connection. And this is, for example, I draw here, you see, solid has a periodic arrangement of atoms, there's a certain structure to it, a liquid or a gas. I'm not that good in animation, so I couldn't make these green dots move around. Okay. Now, the same thing can happen in magnets. So when you call something as a magnet, right, a traditional ferromagnet in which all the spins point in the same direction, there's a certain pattern to it, right? And that can also be ascribed to a certain broken symmetry, that the spins, considering that they can point in any direction, have chosen a particular direction to point. So there's a spin rotational symmetry which is broken. The same thing with an antiferromagnet, which I draw in the yellow and the black arrows, right, up and down. Now, the point is that, uh, so the take-home message that was there from 1937 to 1982 was the fact that orders are associated with broken symmetries. Now, the power of this treatment was that you were able to classify all possible different crystals that could exist in 3 dimensions. And people knew that there were then 230 different crystal classes, which you call as the space groups, which are nothing but the symmetries of the time average distribution function of the atoms. Okay. Similarly, when you wanted to classify crystals with a magnetic structure, you could take the time average current distribution function, okay, which gave you the 1,651 magnetic space groups in 3 dimensions. So the power of this treatment of the symmetry breaking, paradigm was that it was able to give you a complete classification in principle of what could exist in nature. However, nature never stopped surprising us, and the surprise came in 1982 in the form of what is called as a fractional quantum Hall liquid. So with the advent of semiconductor technology, what happened was that people were able to, for example, in aluminum, gallium, arsenides heterostructures, people were able to really trap a 2D electron gas and put it into a strong magnetic field. And then what they found was that there was a new state of matter, which was very weird. It was actually a very rigid, incompressible state of matter, which seemed to be more solid than a solid. And this was the experiment done by Sui, Sommer, and Gossard, okay, in 1982. And this fractional quantum Hall liquid, because it was incompressible, it had a very fixed and well-defined density. And in fact, when you measured this density of the electrons in units of the density of the magnetic flux quanta, you got some very, magical filling fractions or numbers. They were all rational numbers: 1, 1/3, 2/3, 2/5, 5/2, like that, right? So people then started thinking, well, I mean, there's a dichotomy, right? It's a liquid, right? How can a liquid have internal structure? That's what common sense would tell you. But still, the fact that you could have only very fixed and well-defined density meant that there must be some kind of thing going around inside. There must be some, structure or pattern, which gives rise to these, rational, densities of the electrons. So in order to understand this more, let's say in a very hand-waving way, let's try to see what does an electron do when it is put in a magnetic field, right? It executes what is called as a cyclotron motion. It goes around in a circle. Now we know that when a particle goes around in a circle in quantum mechanics, there's associated wavelength. And the wavelength is simply the Planck's constant divided by the momentum. Now, only an integer number of waves can fit in a circle, right? So that leads to the quantization of momentum when a particle goes around in a circle. So if you want to think of it in terms of a dancing pattern, you can say that the electron always moves around in steps when it goes around in circles, right? With a step length equal to the wavelength, and always takes an integer number of steps to go around, okay? That's one thing. But then there is another kind of motion. So when you take a single electron, that's fine. But when you put it in like an electron gas, a system of many electrons, the electrons also go around each other. And we know that electrons are fermions, right? So when you interchange two electrons, you have to put in a minus sign in the wave function. Or so that basically means that, but actually interchanging two electrons is nothing but taking one electron halfway around the other. So the electron takes a half integer number of steps to go halfway around the other electrons. Okay, the half integer is just accounting for the minus sign. And therefore, an electron must take an odd number of steps to go around another electron, right? So there are some, let's say, some restrictions of how you go around. Then of course, electrons also try to stay away from each other. They have a Coulomb repulsion, they have to obey Fermi statistics, and therefore they will try to take as many steps as possible to go around the electron. So we see that the electron motion inside a fractional quantum Hall liquid is not at all totally unconstrained. It's highly synchronized. It's like synchronized swimming, in the Olympics. There's a lot of rules you have to obey. And what Laughlin realized was that actually once you put all these, constraints into picture, there's only a unique wave function without any variational parameter that he wrote down to describe the electrons, moving around in this new state of matter, for which he got the Nobel Prize. Now the remarkable
Can
thing.
I ask already a question?
Sure. Yeah.
So actually, I have two quick questions for us. So firstly, isn't the integer quantum Hall effect also sort of beyond the Landau paradigm? And if not, why? And the second question is, this Laughlin wave function, which probably captures the many aspects of the theory of the electrons, as you were mentioning, is still, if you look into actual overlap with this actual ground state, it might be even 60%, or it may not be. So it's not. So in reality, this is not really the ground state, right? And so in what sense this Laughlin wave function is what kind of things you can take from that, though it may not be the actual ground state of the theory?
Yeah, so as you correctly put it, the Laughlin wave function is a variational state, right? It essentially captures, so when you put the fractional quantum Hall liquid, on say a torus or other geometries, the Laughlin wave function is able to capture many of the essential properties that you can calculate. So these have been related to chiral spin liquids, and when you transform it in the spin language, you essentially can construct parent Hamiltonians for which the Laughlin type state is an exact eigenstate. It essentially basically captures the essential physics that I just explained to you, but it's still a variational state. Okay.
Yeah, I mean, it has no variational parameters. So
there's no variational parameter. That's absolutely fine. It's still a variational wave function when he proposed it. Okay.
Right. So
regarding the integer quantum, sorry, yeah.
Yeah. So basically, it tries to capture some of this.
Sure.
some of the aspect of it explains why it is this rational numbers, the new that you just described. But beyond that, for example, is it like, would you like to say, I mean, it's not like in some sense it capturing physics at certain scales or something, right? It's not like that. It simply gives you the understanding why these are rational numbers, nothing beyond that, or there is some more detailed. I mean, is it like you can trust it at certain scales, or is it something, it has some other kind of utility?
It's a good question. Yeah, I'm not sure I can answer that offhand. I mean, yeah, so I don't, my understanding of, let's say, this is not that deep. I've not worked into this. So let me be frank. So I might not be able to answer your question in all honesty. Okay. But I'll be happy to discuss this actually at some point. Whether is there any scale at which the Laughlin wave function works, or how was it proposed in what context, you know, or what properties were then, beyond the variation level were then captured. But regarding the integer quantum Hall effect, of course, I mean, I don't think the Fermi liquid theory can capture that. So in that sense, it also falls outside the traditional paradigm.
Yes, it's one of this traditional topological state, right?
And in fact, it's not the fractional. Okay, I'll come to that in the next slide, right? Okay, so let me then try to also come back to this. So actually, the thing is that despite the absence of any static, positional order, it's called crystalline order. Actually, the quantum motions of the electrons in a fractional quantum Hall state are highly organized, as you can see from this hand waving picture, right? So the thing is that, so the thing is that there are certain kinds of, let's say, internal orders in fractional quantum Hall liquids, but these orders cannot be described by any, long-range orders associated with some operators, or some broken symmetries. There was an attempt when this wave function was proposed by Steve Gervin, actually, to try to ascribe some broken symmetries to these kind of, ordering patterns. However, the operator he came up with actually was not a local operator. So the correct statement is that there are no local operators, whose expectation values would then give you this kind of, patterns, dancing patterns of electrons in it. So it was realized actually that these, so the thing is that the reason why this falls beyond the Landau's theory is that we are here not looking at, so in the traditional, Landau's theory, when he was looking at crystals, he was looking at the symmetries of a positive probability distribution function of a classical statistical system, which was positive definite, right? Rho being positive. What we are looking here is not at the symmetries of any static order of a classical statistical system, but the symmetries in the motion or the symmetries in the complex ground state wave function. Okay, so therefore the Landau's paradigm is bound to fail for any system when you look at a quantum ground state, because it simply is not built for that. It is built to describe a classical statistical system with an infinite number of variables, which is positive definite, and you just enumerate the symmetries of that. Okay, so let me come now to that. So the order that was proposed, there was actually topological order. So what do we mean by that? So let me make it more concrete. So it means basically that there must exist some quantum numbers, some measurable quantum numbers, right, that are robust against any perturbations. By any perturbation means perturbations which can destroy any symmetry of the Hamiltonian, like putting some impurities, at random. But these orders should be different for different spin liquids, different, fractional quantum Hall liquids. So the fact is that this ground state degeneracy that you have is not a consequence of any symmetry of the Hamiltonian. So the way to understand is the following. You have a ground state, right? A fractional quantum Hall state. What you do is that you create a quasi-particle and a quasi-Hole pair. Okay. Then what you do is that you move the quasi-particle all around the torus, right? And it comes back. And then you annihilate the two. And then you come back to the ground state. Now an operator, let's call it U, that does such a job, that starts from a ground state, creates this pair, moves one around, and then annihilates and comes back, obviously maps ground states to ground states, right? And what you can do is that you can define an operator X, which takes this quasi-particle in the X direction, an operator Uy, which takes it in the Y direction, and then in the minus X direction, and then in the minus Y direction. And you land up with these paths here. Now the point is that if you actually multiply all of these, right, this whole operation is just mapping ground states to ground states. And the tunneling path that you've done, the tunneling process that you've done can actually be deformed to two linked loops that you show in panel D, right? Two linked loops. Now these two linked loops just mean that you're taking the quasi-particles around each other. So what happens is that they accumulate some kind of a statistical angle or a phase factor. So for a Laughlin state with a 1 over q filling fraction, right, you have a statistical factor which is pi over q, right? So this whole operation of tunneling processes, uy inverse, ux inverse, uy, ux, just gives you e to the power 2I theta, where theta is a statistical angle, which is pi over q. Now, since this operation maps ground states to ground states, the ground states form a representation of this algebra, right? Straightforward. Now, this algebra of the magnetic translation group has only a single q-dimensional irreducible representation. That's 4 lines of algebra, you can show that. There's only a single representation which is irreducible and is q-dimensional. And therefore, the energy eigenvalues that you get have to be q-fold degenerate, right? So you see a direct connection between the filling fraction of the Laughlin state to its connection to the statistical angle, to its connection to the degeneracy of the ground states, okay? So that basically means that the 1 over q Laughlin state has q times an integer number of degenerate ground states. So there's a direct connection between that, the quasi-particle statistics and the ground state degeneracy. And this ground state...
Just a quick question. So here q is an integer, but suppose if you have not 1 by 3, but something like something like 5 by 2 or something, or in that case...
So sorry, so suppose, yeah, so suppose you have a Laughlin state in which, so you just take, yeah, so I'm talking about Laughlin states in which you can express something like 1/3, or you have something like,
like 1 by 3, 1 by 5, this
1 by
kind
3
of state.
or something like that. Yeah, just
okay.
for illustration. Yeah.
Okay.
Okay. So in this case, yeah, so just to simplify the argument, right? So in that case, you will see that there is for representation, there's a direct connection between the quasi-particle statistics and the degeneracy. And this degeneracy is actually robust, in the sense that you can put all sorts of things in the wave in the Hamiltonian which break all its symmetries, but this degeneracy will remain intact. So that basically means that the internal orders or the patterns which are responsible for this degeneracy are also universal. And this is what you call as topological order. In fact, the fractional quantum Hall liquid is not the first example of a topologically ordered state. That distinction belongs to the superconducting state, which was discovered much, much before 1911. So contrary to what is usually thought, a superconductor does not break a U1 symmetry. Okay, so there is no symmetry breaking in a superconductor if the electromagnetic field is also taken into account. Okay, so the thing is,
well, can I just say something, ask something, sorry, here. So, yeah, so here, by this quasi-particle, quasi-hole, you mean this exact states, the analogs of the excitations about the ground state, yes, with Laughlin and, okay. Yeah. So if it, in general, is it known that what is this, what kind of representation of this, UY inverse, UX, this, what kind of representation of this operator, this link of what operator should the ground state belong to? For suppose if you have, I think generally you would need something like composite fermion like picture or something.
Yeah, precisely. That is known. That is very well known.
The answer is known. Okay, and yeah, this is known what kind of representation the ground state is. Okay,
yes,
thanks.
Yes, sir. Arun here. Sorry. Yes, what is the relevant Riemann surface here?
Oh, so generally I would take a 2 torus here.
Okay.
So genus 2.
So then G is just 1.
Yeah. So yeah. Okay. Yeah. G is just 1 here, or you can typically here in this example I've taken a 2 torus here. Yeah.
2 torus is genus 2, right? I mean.
Yeah, genus 2.
Genus 2. Yeah.
So yeah. So basically I've taken a genus 2 surface. So I'm moving one around one. So along one sort of tube of the torus and the other along the other tube. The torus.
I mean, you just mean a T2, right?
I just mean
so
a T2.
That just has one hole in it, right?
No, he's taking a double donut like this. It's a genus.
I see.
Like this one, yeah, this one, the one that
I okay, yeah, I see that.
Yeah.
And I think he's moving one around this, around this, and the other around the other.
Yeah, so you can deform these two link loops into these kind of closed paths right here. So you take one around like the let's say if I'm going around a vada, I go around and I come back like here, and the other one is the other way.
Yeah. So I mean, okay. Okay, please go on.
So the point was that actually, yeah, so this kind of state was sort of topological order. So that is basically, so there is some sort of degeneracy that is, not associated to any Hamiltonian symmetry. And the fact is that this, so what this paradigm does beyond, traditional symmetry breaking is to look at symmetries of complex ground state wave functions rather than looking at symmetries of distribution of atoms, some static distribution thing. Yeah. So, okay. So there's a much broader concept which arose, which was of which topological order was only a part of when you had some gapped excitation, which was basically quantum orders. So quantum orders were nothing but, when you didn't have any explicit symmetry breaking in the ground state, so including gapless ones, you could actually define a much larger concept mathematically, which would then include topological order as a subset when you have a gap to excitation, right? So the reason why this was introduced was basically to have the same kind of power as a conventional symmetry breaking description would give you. For example, if you could completely classify all types of crystal orders, you could determine the structure of the low energy excitation without going into the details of the system, like phonons in a solid. There are three modes because three translational symmetries are broken. And the fact that you could have symmetries which could, that you could generate and protect Nambu-Goldstone modes, right, which are the scalar bosonic excitations. So similarly, people thought that you could have quantum orders and a certain projective symmetry group description that could classify different quantum states that have the same physical symmetries, okay? And then you could determine the structure of low energy excitations universally without knowing all the details of the system, right? And similarly to how the symmetries would protect gapless Nambu-Goldstone modes, you can have, gapless gauge bosons and fermions, which could be protected by quantum orders, right? So then you could have, purely bosonic models in which fermionic excitations could emerge. That, for example, I'll come to in the next slides, as long as this ground state had some proper quantum order. So this quantum order was simply just looking at symmetries of the ground state wave function. Okay. So the most, let's say, prototypical example of a state which has quantum order is a quantum spin liquid. So as the word says, it is just a liquid of spins. So in the sense that, when you have spins which are residing at some crystal lattice points, they don't freeze into any particular orientational order, right? They keep moving around in all directions. So if you take a time average, it basically goes to zero. So it's just a liquid of spins. So more thing, if you take a spin operator, therefore spin 1/2, and you calculate the expectation value in a certain, ground state, a spin liquid state, that will be identically zero. So a state in which spins continue to fluctuate and evade order down to 0 Kelvin. What experimentalists would say to temperatures which are orders of magnitude smaller than the typical energy scale of interaction, the exchange energy scale. So the natural question that arises is that under what conditions can you destabilize orders and realize a liquid-like state? So what is the, what sort of, ingredients do you need to destabilize, conventional orders and realize liquid-like? How do you melt? How do you melt magnets? That's the question. So the simplest thing that comes to mind is actually frustration. So what you do is that you try to put spins with interactions, and which purely because of geometrical reasons on the crystal can never be satisfied. So if you take a triangle, right, and you take easing spins, and they all want to be pairwise anti-parallel to each other, then you will see that one bond will always be unhappy. Okay. And you can draw many such configurations. So there's like energetic degeneracy, and you can fluctuate within this ground state manifold, right? And the system remains confused. It doesn't know what to do, right? And basically it tries to suppress any tendency towards ordering, right? So the simplest way to do it is to take any, odd-sided motif like a triangle and do either a corner sharing arrangement or an edge sharing arrangement and land up with some kind, say a triangular lattice or something. Okay? So the thing is that what Anderson envisioned was that if you take a triangular lattice and you put these, spins, say Heisenberg spins, so which can, continuously point in any direction, the simplest arrangement, what could think is that if you want to build a non-magnetic state, so a state in which has no net magnetic order, which is what we want, the easiest way is to pairwise put them in singlets, right? And then to arrange these singlets, as you see in panel on top. Right? However, such a state breaks some symmetry, it breaks translational symmetry, right? And it's sort of ordered in that sense. So what he thought was that you can actually construct various different configurations of these and make them resonate among each other. And these bonds need not, these singlets need not even be just short range or nearest neighbor, they could be arbitrarily long ranged. So a spin liquid can actually be just thought of as a linear superposition of these various singlet configurations which are resonating, right? And the whole system has known well-formed net magnetic moment. When these are only short range, of course, it takes a certain energy to break these and create excitations, right? Which is order J. And at nearest neighbor, the J is typically strong. So you need a certain energy above which you can then crack them, right? So there's an energy gap to excitations. Whereas when you allow them to be, very long ranged, they can actually, you need a very tiny amount of energy, and the thermodynamic limit, its system becomes essentially gapless, right? So you have broadly two kinds of spin liquids, those with short range, resonating valence bonds, and those with long range, right? And the whole mathematical classification of, of trying to, enumerate what are the different types is just to classify patterns of long range entanglement. And this is what projective symmetry groups does, right? So let me come to that. So let me take a step back and delve a bit on actually where this origin of a spin liquid concept came back. So it came, in the 1930s, when, after quantum mechanics had been invented, Neil actually proposed this standard up-down arrangement of, spins to define the ground states and to explain, certain magnetometric and calorimetric data on various systems that were thought to be, could be done with this kind of a model of a two sublattice, where you have two kinds of sublattices, either spins are pointing predominantly up in one or predominantly down in the other. However, this model immediately came, was greeted with skepticism. And one of the greatest skeptics was Landau. And his argument was that if you correctly apply quantum mechanics, right, to this system, this would lead to fluctuations which will completely randomize this order. And that's very straightforward to see. So when Heisenberg proposed his spin Hamiltonian, SI.Sj, this is the simple SI.Sj, he did it for a ferromagnet, okay? So that is in which all spins are in the same direction. And when J is negative, you had SI.Sj, okay? So the spins try to be parallel to each other. That's fine. However, when you try to generalize to an antiferromagnet, you clearly see that this kind of a arrangement can never be the ground state of this Hamiltonian. The reason is very simple. You write it as an SZ, which is like the easing part, plus 1/2 in terms of the raising and lowering operators, right? You can do that. Now you see what devastating effect these raising and lowering operators have on such a kind of a cartoon picture. So if you have up, down, up, down, up, down, and you apply S minus S plus on this, you see what happens. You reverse one spin and reverse the other one. And what do? You basically reverse two spins and you create two excitations which decrease the sublattice magnetization. So if you were to add up the magnetization, say 1/2 times every alternate spin, so you'll have 1/2 times n/2, right? Total number of spins, half of them are up, half of them are down. The total saturation magnetization should have been just 1/2 times the number of spins in one sublattice, right? You clearly see that it creates actually a fluctuation. So that is what is called as a 0-point fluctuation in a quantum antiferromagnet, which reduces its sublattice magnetization even at zero temperature, right? Now, the thing is that in one dimension, you can show that actually the reduction in the sublattice magnetization at zero temperature, that is the change in the total SZ component from its saturation or nominal value, in the language of, if you do a Holstein-Primakov transformation, in terms of its bosons, is the expectation value of this B dagger B, right? And that can be evaluated. And you see in one dimension that has a logarithmic divergence, telling you basically that the correction to the sublattice magnetization is divergent. Or in other words, there is no long range order in a 1D antiferromagnet, even at zero temperature, okay? This later was more sophisticatedly cast as what is called as the Hohenberg-Merman-Wagner theorem. But it's basically a phase space argument which was already known and written up by Peierls and Landau in the mid-30s, that there is no long-range order in 1D, there is no phase transition, okay? So what happens that in 1D, you naturally have a spin liquid. So when Hans Bethe actually solved the system of a one-dimensional chain of spin 1/2s, which are interacting antiferromagnetically at nearest neighbor, and got by the Bethe ansatz and got the full eigenenergy spectrum and got the, the wave function, he had actually discovered the spin liquid. But the only problem was that it took a long while, actually a good 5 decades before all the properties, all the correlation functions, of this kind of a state were all completely explored. And, it was known that, the system lacks any long range, magnetic order, and it's actually a spin liquid. So the thing was that the origin of the spin liquid idea, it was through 30s and 40s. It was only in 1949 when neutron scattering experiment by Schull discovered, these sublattice structures, that the Neil was finally vindicated. And it was only then that, people believed in the existence of antiferromagnetic order. However, there's no frustration here. All that was needed was the fact that you have 0-point oscillations whose amplitude can become divergent, right? Which can completely. In fact, till this date, there is no proof of the existence of long-range antiferromagnetic order, say on a 2D square lattice. So if I put up-down spins on a square lattice, right, there is no analytical proof that it's long-range order. There is numerical proof, which is very strong from quantum Monte Carlo. It's numerically exact, but there is no analytical proof. And that is why when you calculate the sublattice magnetization of an antiferromagnet, you see it's always reduced from its nominal value. Okay. So the history of spin liquids and the first ideas already were brewing in the 30s by people who were skeptical and thought that this cannot exist. However, the question is that in 1D, dimension does the job for you. You produce a logarithmic divergence, you're done. But defeating the Néel state in higher dimension was a challenge that came next. And this was picked up in the 80s, more so in the 90s and more recently, where people thought that you can also frustrate the system by adding second neighbor interaction. So the diagonals of a square, which are also antiferromagnet, which will of course try to make these two green bonds, which are happy, also frustrated. And people started parametrically frustrating the systems. There were experimental materials which were thought to be close to these kind of settings. And of course you then had the geometrically frustrated lattices, like the triangular lattice. So if you take not Ising spins but Heisenberg spins, Anderson first proposed in 73 that such a system, quantum fluctuations would destroy its order.
Sorry,
because,
Yasir,
for example,
could you explain the frustration a little bit more? Like why do you call it parametric frustration?
So parametric because you just say if you take nearest neighbor interaction, so you take let's say a green spin, all the other nearest neighbor spins want to be anti-parallel to it. That order can be realized on a square lattice perfectly happily without any problem, right? Now, of course, there are 0-point oscillations which will reduce it and can also wash it out like in 1D. We don't know. But it was realized and it was proven, say numerically, that this order is generated on a square lattice. Then how do you frustrate it? You add a second neighbor interaction which connects the diagonals, right? Which is also antiferromagnetic. So which tries to make it antiferromagnetic, right? So you clearly see that this will frustrate the J2 bond will frustrate the J1 bond, right? Okay.
Yeah, but still, like in a square lattice, the distance between the two green ones and the distance between, say, a green and a red is the same, no? Or that is the point that they have the same distance. I don't get that.
No, the diagonal of a square is square root 2, no? On the one side,
yeah,
it's 1.
Yeah, that I understand. But here it is a diagonal has the same length as the.
Yeah, I just drew it schematically, I just.
Okay, sorry. This is why I got confused.
I'm sorry for that.
Sorry.
Yes, sir.
Okay, but the point was that you can basically create a disordered randomize so the thing is that at this high point of frustration, you can actually people later realize a spin liquid that the system becomes so frustrated it doesn't know whether to satisfy the J2 bonds or the J1 bonds, and in between there's a region where you stabilize a spin liquid.
Okay, same so Palki has a comment anyway.
Yasir, are you saying that the 2D with Ising spins, you can't get a 2D antiferromagnet?
No, I'm saying Heisenberg spins. Heisenberg.
Okay.
No, Ising spins also. Thank you for pointing this. So the Ising term is actually very innocent. It does nothing. The SZ, it has no quantum fluctuations.
Right.
So it's just an energy cost, right? So it doesn't flip anything. When it acts on a state, it just gives you an energy cost times the same state. So So let me thank you for pointing this out. The Néel state is an eigenstate of the classical Ising model. There's no problem there.
Right.
The problem is caused by these plus minus terms, which only arise when you take into account the Heisenberg nature of spins.
Okay. Yeah.
Okay. So there they can completely wash the order out. So right now I'm talking about, I come back to Heisenberg spins.
Yeah, sir, can I ask
in case of Heisenberg?
This is Raj.
Sure.
Can I ask a silly question? So, of course, your argument just tells you for the Heisenberg model in 1D with antiferromagnetic interactions, there is no long-range order. That's all it says, right?
That's all.
It doesn't tell you about anything about whether whether it's a spin liquid state. It doesn't say anything about that. It doesn't say anything about what the spin-spin correlation function looks like.
Absolutely right. There is no static, the spins do not freeze in any, let's say, long range up, down arrangement. That's all it says.
Correct.
Yeah, it's a disordered state. So the correct way is it's a paramagnet. I don't know the nature of the paramagnet right now.
Correct.
From this argument.
Yes.
So this is a simply phase space argument, right?
Right.
So just generating in 2D, so you will have at finite temperature, you will have worse than logarithmic divergence. That's what, at finite temperature in 2D, you cannot have long range order.
And the whole point of the fact that you have a antiferromagnetic sitting in there is the 1 over Q. That's it.
It's a 1 over Q, right? That comes from the linear dispersion.
Dispersion, exactly.
That comes from the dispersion relation. Yeah. Okay. Very good. So we realize that already antiferromagnetism, the concept of antiferromagnetism is actually not that straightforward. It's plagued with doubts. In 1D, it cannot be realized. There is no such thing as a 1D arrangement of up-down spins, of Heisenberg spins. Okay. And at the moment quantum mechanics enters into the picture, as per Landau, the correct application would lead to complete washing out, which is what happens in 1D. In 2D, things are better off. Of course, at finite temperature, again, you have even worse divergence, you have worse than logarithmic, okay? So, but at zero temperature, what can happen is that you can still realize some kind of an ordered arrangement. So the best you can do, for example, on a triangular lattice is to make the spins point at angles of 2π/3 with respect to each other. Now, if you calculate the energy of such a state, okay, by simply just, cosine of 2π/3 times 1 over 4 times nz/2, simple exercise, you get a certain number. Fine. However, if you say, no, I don't believe that the triangular lattice can order, it's frustrated, it must be a spin liquid, and you try to pair these spins into singlets, and you cover them by these dimers, these singlets, which are non-overlapping. So of course, each side is part of only one singlet, you actually get the same answer. So who's right? Is the system ordered? Is the system disordered? Well, the answer is when you now introduce quantum fluctuations into the system, they will of course reduce the energy of the antiferromagnetic state. It's not an eigenstate of the exchange Hamiltonian. Okay, I come back again. The antiferromagnetic state, the correct picture of the ground state of an antiferromagnet is not this thing that we are taught. Okay, it is actually an admixture of states with different number of spin flips. Okay, it's a hodgepodge of a different number of spin flips. And since it's not an eigenstate, how can it be the true ground state, right? So the thing is that when you add quantum fluctuations, you always gain energy in 1 over s. If you do a 1 over, so if you start from the classical limit, which is formally taking the spin length to infinity, and then you make the reciprocal spin finite, the leading order correction to the energy will always reduce it from its classical value. Okay, you will gain. But so you will gain also the energy in the valence bond. You make them resonate. A resonance is a process in second order perturbation theory, and second order perturbation theory comes with a minus sign. You will also gain here. So this was a long-standing question, and in fact, it was in the late 90s, where actually it was then very thoroughly shown that Anderson's conjecture was not correct. The triangular lattice is in fact ordered. It orders in this 120-degree arrangement, as I show here in the blue thing. Okay, the spins are at 120 degree in every triangle, right? And yeah, it took a long while before actually this was shown numerically. That this is ordered, and the sublattice magnetization is considerably reduced from its classical saturation value, telling you that quantum fluctuations are very strong. It's actually just, I think, 40% of its total value, saturation value. Okay.
So sorry, Yasir, for such a state, the ground state, the entropy is 0. The entropy at absolute 0 is 0, therefore.
For which state?
Once it's ordered in this 120-degree arrangement, it's a unique down.
Yes, that's right. Yes, that's right. Yes.
So the residual entropy does tend to 0.
The residual entropy does tend to 0. It becomes let's say, a traditional ordered state.
Okay, thank you.
Yes. Yeah.
And what about the spin liquid state that has 0 entropy at 0 temperature?
No, the spin liquid keeps fluctuating. The entropy does not tend to 0. It's not a unique configuration at 0 temperature.
So, okay.
Yeah.
Because it has many gapless states, of course. If it is gapless,
yeah.
then it has to.
Yeah, precisely.
Just one more question to ask is, in case of 1D, we have some examples like AKLT Hamiltonian, which can be exactly solved. And we can get some insights from it. Are there some analogs in 2D?
Yeah, the most celebrated example was given by Kitaev. It's called the Kitaev model, which was exactly solvable.
Right.
It is basically consists of a tri-coordinated lattice, say the honeycomb lattice. So you have a coordination number 3, and each component of the spin interacts with the same component along given bond. So it's like on one of the bonds, it's like sigma X polymatrix with sigma X, on the other sigma Y, and the third is sigma Z, sigma Z. It's an anisotropic model, but it's exactly solvable. Yeah.
Thank you.
Yeah. So
Yasir, how complicated is this 120-degree picture? I mean, so suppose I was to write the state, is it? I mean, is the entanglement structure, say, a simple one? Because it looks like that to me.
no, it's a very simple one. It's a trivial product state. Let's say it has no long-range entanglement. It has only short-range entanglement.
I see.
Yeah.
So this is an exact ground state, and this is known only numerically, is it?
This is known numerically. There's no analytical proof for it. No.
Well, that kind of sounds strange, right? Why is it that such a simple state, which you're saying is something which is simply a product state, why can't one show that? So I mean, so what is the difficulty that one can't show that this is the ground state or just any state?
No, one can't show that this is the ground state.
Okay, so I mean, it's easy to see that this is an eigenstate, but not that it's a ground state.
Not that it's a ground state. Yeah, and the ground state, as I told you, is very difficult because it's an admixture of states with different number of spin flips because of these plus minus terms.
Sorry, you are saying then that this
picture model is a high.
So you're saying this product state picture is only approximately true, because if you have spin flips, then it is.
Of course, yeah. No,
it is a superposition of different.
Yeah, of course, it's a superposition. So it's not. So you cannot. So it's very difficult to write down an exact antiferromagnetic wave function for the state.
So there has to be some entanglement. Then it may not be short range. It may be short range, but still there is some.
Yeah, that's what I said. It's short ranged.
Yeah, a short range.
So then, should I kind of think about it like a Majumdar-Ghosh 1D ground state, which is a simple combination at the Majumdar-Ghosh point?
Yeah, at the 1/4 point. Yeah.
So, I mean, there it's a simple superposition of two RVB states.
Yes.
So
yeah.
would I think of this state as something like that?
No, so here what is happening, as I said, is that basically you are so every, say, if you add up all the spins, say all the black spins or the blue spins or the red spins, right? The thing is that their sublattice magnetization doesn't add up to, say, the total value that it should be SZ, right? It's reduced, and it's reduced because of these fluctuation terms, right? So the thing is that, of course, I can write down an exact wave function on a finite cluster by numerically diagonalizing the state, right? So if I do Landau or something, I can of course write down. I can converge to the exact state. I can give you a wave function.
Sure.
Yeah, that's possible.
What I'm I think the point is how close is that state to this state which you have written on terms of the
this is just a static frozen picture I'm showing. It's a snapshot.
It's I think the point is that because the spin flip can only be very local, because the Hamiltonian is local.
Yeah.
So you will find only very long distance spin flips or very large number of spin flips highly suppressed. So approximately this picture is true, but then on top of that, you will find some systematic corrections maybe.
Yeah.
So Yasir, would it be fair to say that this is the picture that one would get for this Hamiltonian in the largest limit?
Precisely. This is a semi-classical picture.
This is a semi-classical picture, right? That's what you're.
So all these antiferromagnetic pictures that we draw, if you formally take the spin to be very large, like 10 or 15 or, going to infinity, let's say, formally speaking, that's when it becomes like an exact picture.
But Yasir, this is Suresh, that can't be true, because even if you take your frozen picture, there is 3 factorial. I mean, I can draw 3 factorial, exchange all the blues.
Of course. Yeah. So of course there are accidental degeneracies in it. Yes, I can rotate about the center of this black thing as an axis, and then of course I will preserve the 120-degree structure, and nothing will happen. These are accidental degeneracies, which are sorry,
Yasir, the point is, this is a quantum model. It's a quantum spins in 2 dimensions. Now, solving it exactly is like solving a 3-dimensional classical spins problem exactly.
Yeah.
So it's not possible with quantum fluctuations included.
But you can solve it numerically.
Yeah,
you can solve it numerically. Yes, I can diagonalize it.
With the exact ground state, you need to solve the problem exactly, and that can't be done.
No, what I'm saying is that if I take a finite cluster, right, and I were to diagonalize it by Langshaw's procedure.
No. I understand. It will converge as the size goes. You may even be able to show that it converges to some limit.
Yes.
But the point is, it's not an exact solution analytically.
No, it's not.
Yeah, that's the point.
Yeah, it's not. It's not. Then of course there are accidental degeneracies, but they're not from apart from the global SU2 spin rotational symmetry. There are of course additional degeneracies that arise. Yeah. Okay. But then these are lifted by quantum fluctuations. So this is talking about in the classical limit. And then of course, when you do 1 over S, then you can have certain structures which are selected. Okay, so there are various ways of defeating the Néel state. We saw one of it. You can do frustration. You have small values of spin, which makes it more quantum mechanical, which leads to more 0-point oscillations. There's another very interesting way. You can have under constraint systems. So let's take a simple example. So you take a lattice, which is formed by some corner sharing arrangement, let's say. So let's take what I call as a pyroclo lattice, which is formed by a corner sharing arrangement of tetrahedra, right? Now, suppose there's a spin sitting at every vertex, right? Now, let me ask, how many degrees of freedom does the system have? So it's a classical spin, right? So let's normalize the length to 1. So suppose it's an n component spin, right? N component spin, and there's a normalization condition. So the number of free parameters n minus 1. Okay. Now let's take a plaquette. So this is like a tetrahedra. So it has 4 edges, but you can have a general mathematical thing in which you have q edges, q corners, right? And then you have n such blocks, tetrahedral blocks. But each such blocks, they're shared. Each vertex is shared between 2 such blocks. So the total number of degrees of freedom is n minus 1 qn divided by 2. Fine. Simple Maxwellian mechanics counting argument. Then I ask you, how many constraints do you have? So if you look at such a simple Hamiltonian, SI.Sj, at a classical level, right, you can always rewrite it as a complete square over as a disjoint sum of the total spin on every such tetrahedra squared minus a constant. So it's just S1 plus S2 plus S3 plus S4 squared minus a constant. So if you expand this, you of course get the cross terms, which is the original Hamiltonian, and you must subtract the S1 squared plus S2 squared, these constant terms, right? And the over 2 just tells you that about the double counting. Now from this, it is very clear that any state which satisfies this constraint, that the vector sum of the spins on every tetrahedra must be 0, is a valid ground state. That's the only criteria a spin configuration must satisfy to be a ground state. Right? I'm taking say some n components, right? Fine. So of course, the number of constraints k that you have is simply the number of tetrahedra times the number of spin components, because component by component you must get 0. All the x components must add up to 0 of the 4 spins. All the y components must add up to 0. All the z components must also add up to 0. So you get n, which is the number of spin components times capital N. Okay, now real spins in nature are all Heisenberg, let's say physically, right? So you put n equals 3 in this thing. And the highest coordination you can have in 3D, let's take it's q equals 4 tetrahedral units. You put it there. What do you get? You get that f minus k equals n. That means the system has an extensive degeneracy. As you keep on adding more and more tetrahedra, the degeneracy keeps on growing, right? So that basically means that there are local degrees of freedom which can fluctuate independently without the system leaving its ground state manifold. Okay. So this is a remarkable feature. You put in all the constraints and you still have an under constraint system. And therefore you can easily see that I can construct many spin configurations, which all add up to 0 on every tetrahedron. I can make 2 up, 2 down. I can make 2 in, 2 out, like that. So you can have various, plethora, and this is actually infinite. It's exponential order L cube. Okay, the number of configurations. So the entropy is, is extensive. Now the thing is that when you have such a large manifold of states at 0 temperature, it's very interesting to explore what happens when thermal fluctuations come into, when temperature becomes non-zero. And this leads us to the famous order by disorder mechanism. It's a very strange name. So the thing is that all these states are not connected by any Hamiltonian symmetry. And therefore the spectrum of low energy excitations around this manifold will be different for each of these states. And thermal fluctuations will select that state which has the highest density of low-lying excitations. And this is the famous order by disorder mechanism that in fact, when you add thermal fluctuations, which are actually disordering, You don't disorder the system, but you make it select out of this entire manifold of states, you make it select a particular state, which has the highest density of low-lying excitations, or magnons, as it's called. Okay.
Sorry,
This can happen.
one trivial question. So at t is equal to 0, why the same logic doesn't apply? Because you also have an entropic factor, no?
No, okay. So I'm taking two accounts. First, we are at classical. So let's say the spin goes to infinity, 1 over s is 0. The other is temperature 0. Temperature can do this job, but so can also thermal quantum fluctuations. So when the reciprocal spin becomes finite, okay, the
I
same
see,
thing can,
okay.
same thing will occur. That's the quantum order.
Okay, so if at finite s, of course, quantum fluctuations will also play a role, not only thermal
play a role. They will
fluctuations.
select, but the selection mechanism is a bit subtle. In the case of thermal fluctuations, you will select states with the highest density of low-lying excitations. In the case of quantum, you will select states with the lowest average magnon energy. So you will select both states, but the selection criteria will be a bit different. In fact, it was shown actually in the late 90s by Roderick Mersner and John Chucker that thermal fluctuations fail to lift this degeneracy down to temperatures they showed around 10 to the power minus 4 J. Okay, and therefore it realizes what is called the classical spin liquid, and it has highly non-trivial correlations, highly non-trivial. So you can already see it in the sense that if you treat this pyrochlore slab wise, and you want to impose this constraint, the moment you fix the spin configuration on one slab, the next one is automatically determined, the next one is automatically determined. The correlations start propagating, and you have
So
beautiful, dipolar correlation.
just a simple question. So are the tunneling amplitude finite in the zero temperature limit, in the thermodynamic limit and zero temperature?
Yeah, there are no internal energy barriers. You're free to move.
Even in a thermodynamic limit. So in that case, why you have so essentially you typically expect a unique ground state, right? Because you can tunnel through all of these configurations.
No, there are no internal. Why would you expect a unique? I mean, you have a manifold of states which is extensively degenerate.
Yeah, but this is a classical picture, right? And then you say that
Of course.
classical picture largest limit, but quantum mechanically you can tunnel without
yes. Yeah. Quantum mechanically, right? Yeah. There are tunneling processes. That's right. Yes.
Yeah. Then typically you would expect a unique ground state.
Of course. Quantum. Yeah. Okay. So when you add, to go into a bit more detail, when you add quantum corrections in 1 over s, you lift this extensive degeneracy and it becomes sub-extensive. It becomes order L. You select a set of collinear states. And then you can go to quartic order in the boson operators, and then you select an even smaller subset. And it's an open problem. It's one of the most challenging problems which is unsolved, is what happens in 1 over s expansion to this selection effects. Actually,
I see.
But really an outstanding problem. Chris Henley attempted to do this. He had for over 2 decades, but ultimately couldn't solve it. It's still an open problem.
Yeah, but there are many things you may not be able to see just simply doing this perturbative corrections, right?
Of course.
I see. Okay.
Time doesn't have, but functional RG has some answers to some of these questions, but I don't want to comment on.
So you're saying that the understanding of the quantum fluctuations is not very well understood, but the understanding of thermal fluctuations is more tractable.
Yeah, because you can apply classical Monte Carlo, which is numerically exact.
I see. Thank you.
Yeah, so that's why. But you have the sign problem here in this quantum Monte Carlo. So of course, when you want to defeat the nail state and melt, there are various ways. As I said, spin can be low. You can have under constrained systems. A good degree of the measure of degree of frustration is given by the fact that. So if you take a Heisenberg Hamiltonian and you write it in Fourier space, so you just take the Fourier transform of all the exchange couplings and you have the Fourier transform of the spin operators. Classically, let's say, all you have to do is to find the set of Q points which minimize G of Q, right? And typically for ferromagnetic or antiferromagnetic orders, this is a discrete set of points, one on other symmetry related points. However, for frustrated systems, it's not a unique point. You can have a continuous manifold, you can have a continuous manifold of Q vectors, in the Brillouin zone, which all, yield, the same energy, okay? So for example, on the square lattice at the highly frustrated point, you can choose any Q vector along the entire line in the Brillouin zone, and you'll have a valid ground state. Same for the face-centered cubic lattice. You can choose any Q vector residing on these lines in the Brillouin zone, and that will give you the same energy. You can have even more elaborate situations where an entire 2D manifold, you can choose any Q vector, and that gives you the same energy, and you can have beautiful, surfaces like the Schwarz P surface, with Euler characteristic -4 here. And you can have, very highly frustrated systems like the Kagome or the pyrochlore, where you can choose any point in the whole Brillouin zone, and basically it gives you the same energy. So the higher the manifold, the higher the dimensionality of the manifold, the more frustrated the system is. That's in some sense how to, you can quantify this. So now the question comes is, after describing all of this, do quantum spin liquids really exist in nature? Okay, so what's the state there? So where should you be looking for? So ideally materials with, spins on lattices that, frustrate conventional nail order like triangular, Kagome, all these geometries. Then you look at spins, spin values which are towards the more, limiting small sites, spin 1/2, spin 1, because they're least classical. And then of course, the lower the dimensionality, like 2D as opposed to 3D, the fluctuations will be enhanced. So these are the kind of ingredients that you're looking at. Right?
Yeah, Yasir, can I interrupt one? So the thing is that how much time you would more need, just to understand?
Oh, you told me 1 hour 15, which is
Yeah, so certainly you could take 20 more
difficult.
minutes without any problem.
Okay.
No, what I'm
Okay.
saying that
Okay.
it may be, I'm just suggesting we can actually continue this later. You're like have a part 2 of it, rather than rushing through topics. You could probably take it slow and then we could finish it at another time.
Yeah,
what do you think? Huh?
Okay, yeah, let me see how I do in next 15 minutes. I think I should.
Yeah, so 15-20 minutes, and because otherwise it might become a little bit too stretched.
Sorry for this. I'm going too slow. I mean,
no, it's fantastic because we are learning things. So I would suggest that rather maybe we could continue, have a shorter version of this sometime soon.
I think we should do that so that we can take it leisurely. Yeah, it's very useful. So Yasir, please.
Yeah. Okay. So you have.
Don't try to rush. Please go at your speed. And if it's left over, let's have a second session if it's all right with you.
Okay, very good. So then the most celebrated example that, really came into prominence around 15 years back was this system Herbert-Smithite. It forms actually these Kagome layers, these pink ones you see here with these blue dots, right? The blue dots are the copper ions, right? They supply the spin 1/2 moments. These are copper 2+ ions, okay? And then the thing is that all these gray dots are these zinc ions, which are non-magnetic. And they lie in between the layers and they essentially decouple them, okay? So you have a system which is effectively 2D and it forms a perfect Kagome geometry, okay? And you have spin 1/2 moments residing. And this is a corner sharing arrangement of triangles as opposed to edge sharing, which gives rise to a triangular lattice. So as opposed to the triangular lattice, which has actually turned out to be ordered, the Kagome lattice now has been shown both theoretically as well as in experimental realizations to be the cleanest example of a model which gives you, where a Heisenberg antiferromagnetic Hamiltonian gives you a ground state, which is a quantum spin liquid, okay? This is the way you see it in neutron scattering is, if you were to scatter neutrons at certain, energies, okay, and you would track the response at various momenta, then if you draw a Brillouin zone, okay, you'll see no sharp Bragg peaks. You see some sort of a homogeneous continuum. Okay? This is related to fractionalization, possibly I'll come later. But then you see, so as opposed to a conventional magnet, which will scatter back neutrons at certain momenta, a spin liquid basically would give you a completely featureless profile, okay? However, so recently there's been a very nice paper by our own Panchanan, trying to do a very nice NMR study, which is published in this Nature Physics, arguing for a gapless ground state in this Kagome antiferromagnet. However, there is, of course, an entire different school of thought where people argue that this entire low energy spectrum is dominated by impurities. It could actually be a random singlet state, which is, a trivial product wave function. Is not a spin liquid. There are arguments by Chandra Verma that actually it's a marginal Fermi liquid, and there are various schools of thought. But let's say we would like to believe that this is a quantum spin liquid. If you're into this field, it's a big argument, whatever, but okay, that's one thing. Then there are some bilayer systems, calcium chromate, in which my collaborators worked in Berlin. These are systems in which, for example, as I saw, you see here on the right-hand side of my mouse, I drew a triangle. So these are bilayer systems in which one layer is predominantly antiferromagnetic. So you have this 120-degree order of these spins you see in the blue triangles. And one layer is predominantly ferromagnetic. right? So you see all the spins are pointing in the same direction. And these two layers are coupled by some antiferromagnetic interaction. That frustrates the system, really. And in fact, there's been, a neutron scattering study of the system, which again found a rather homogeneous distribution of intensity, no, Bragg peaks, and then some functional renormalization group calculations by modeling the system, and indeed found excellent agreement with, the susceptibility data and modeling, the neutron scattering profile. So these are Kagome bilayer systems, So the Kagome seems to be the theme. Then there's a
So this
work.
was your paper
No,
on,
this is my paper.
functional
No,
functional
no.
RG? No, this was.
Yeah, no, I didn't do the RG. I'm not part of that paper. I'm part of this one here, which appeared this year, where we found another, very interesting arrangement of corner sharing these red colored motifs, which is what is called as a hyperkagome. It's just a edge sharing triangles, but in 3D. Okay, made more frustrated by these dangling triangles, which are also, hanging around on this. And this, by a series of sort of thorough studies, by various methods, was shown to lack any kind of, long range signature. There were no signatures of long range magnetic ordering down to temperatures which are, say, 2 orders of magnitude smaller than the leading exchange scale. Okay. And so this work of us was in combination with experimentalists in Berlin, with me doing the functional RG calculations, and our own former MSc student doing neutron scattering, Shravani, and other people, doing magnetometric, calorimetric, measurements. And after a long time, this was finally published, and this is another candidate thing. And the most striking thing that has come recently is that even when you increase the spin value, I already told you, when you increase the dimensionality, right, quantum fluctuations decrease. So there's no logarithmic divergence. That's why we all exist at finite temperature in 3D. In 2D, it's a problem. But when you increase the spin, you also decrease the quantumness of a system. But actually, people have found a one quantum spin liquid. It was synthesized in the group of Bob Kawa at Princeton, the neutron scattering done by Kevin Plum and the group of Colin Boham, others, which also identified a beautiful spin liquid in this system, where you have the nickel 2+ ions, which provide the spin 1 moments. And much remains to be understood about the microscopic origin of this spin liquid in these systems. So there's a lot going on in terms of both materials, but what is lacking is actually from the theory front. So okay, so describing this brings me now to a separate sort of section in my talk, which is to do with the idea of fractionalization, which is the hallmark of a spin liquid, and the origin of its gate structure. So this is where it starts becoming more technical and mathematical. So the thing is that spin liquids have what is called as supposed to feature what's called a spin charge separation. So you can either have pseudo spin charge separation, which basically means that the electron is thought to fractionalize into 2 quasi-particles, one which carries its spin but has no charge, and the other has no spin but has charge. They're called spin-ons and holons. But there could be long-range interactions, possibly confining between the two, which just means that the gapless excitations cannot be described by free fermions or free bosons. And this is what are called as algebraic spin liquids. They feature pseudo spin charge separation. There's another class of spin liquids called chiral spin liquids, which break parity and time reversal, but preserve the product of the two, again found by Kalmer and Laughlin in the late 80s, in which there is actually a true spin charge separation. Because of Chern-Simons term, you have actually a gapping out, and you have a short range interaction, which is mediated by the gauge fields, right? And then you have actually well-defined quasi-particles. So the gapless excitations, can be described by free fermions or bosons. The point of
what is the chirality here coming? What is this chirality that you're talking about here?
So the chirality here simply means that, okay, it'll become clear when I go to projective constructions. It just means that parity and time reversal symmetries are broken in this system. So in the sense that the system features a finite scalar spin chirality, a long range correlation between scalar spin chirality. So if you take a triangle and you calculate SI dot SJ cross SK, okay, and one triangle and you do it on another triangle far away, there is a long range correlation between scalar spin chirality. That's what it means in the spin language. In both these cases, it basically means that the electron operator is not a good starting point to describe these states. So what you must do is to basically cut the electron operator into various parts. And these are called as the parton operators, okay? And this is the origin of the gate structure. The thing is that since you've changed your language from the electrons to partons, right? and you've cut down your electron operator into various quasi-particle operators, you can do certain transformations between these quasi-particles, between the partons, that actually leaves the physical spin operator unchanged. And since any Hamiltonian is only built out of physical, electron operators, this symmetry acts internally within these operators, and therefore it's a gauge symmetry.
And this gauge group has, and this gauge theory should always be confining, because
not necessarily.
Not necessarily. So you can. Oh, so there can be. You can also think of deconfined partons, but then.
Of course. This is the whole class of Z2 spin liquids, where because the Z2 gauge field is gapped except at the critical point, right? And therefore it mediates only short-range interactions between spin-ons, or these quasi-particles, and they behave essentially like a free spin-on gas. Okay, so I'll come to that. So the thing is that in the language of spins, so I'm not much interested into charge, right? The charge degrees are frozen out. I'm assuming, that I'm only interested in the spin degrees of freedom. There is a beautiful gauge structure that emerges. The thing is that you can rewrite the spin operators, every component of it, in terms of certain quasi-particle operators. Okay, these are called spin-on operators. Okay, these are just complex operators. They're complex fermions, F up, F down transpose, and you can just write it as a bilinear. This was first written down by Abrikosov when he was solving the Kondo problem, the scattering of electrons from a magnetic impurity, right? And to exploit diagrammatic techniques, he basically rewrote the spins in terms of fermions. Okay, so these are spin-on operators. They carry spin 1/2, but they have no charge. Okay, so they have no charge, but they have only spin. Now the thing is that when you formally rewrite this expression here, this is fine. All this tells you is that the commutation relation obeyed by the spin operators is also obeyed by the right-hand side, by the fermion operators. They also obey the same SU2 algebra. Fine. But the important thing is that they act on different Hilbert spaces. The spin operator act on the C2 Hilbert space, okay? Whereas the fermions have a 4-dimensional Hilbert space, okay? Up, down, up, and up, down, okay? Now the thing is that you can, 2 lines of algebra tells you that the spin squared can be written as 3/4 n times 2 minus n, where n is the occupancy, the number of electrons per site, okay? And you clearly see that it is only for, so when you are dealing with spin 1/2, n must be equal to 1. Because when n is 0 or when n is 2, you have states which are unphysical. They carry 0 spin. Okay. Now the key observation made by Wen was the fact is that you have some additional symmetries which are present in the Hilbert space, in the spin-on Hilbert space, when you do this rewriting, okay, which are not present in spin space. And you can trivially see, one is that you can basically rotate by a phase factor all these spin-on operators. So F alpha is just e to the power I theta F alpha, right? This doesn't change anything. This is a rotation you do in spin-on space, which keeps the physical spin operator, every component of it invariant. And then you can also do a particle hole transformation. So this sigma just means up or down, and this capital sigma means plus or minus, depending whether it's up or down. And if you do this transformation, again, you can verify it by a few lines of algebra that basically it'll make this equation in the red box unchanged. Okay. So the thing is that when you go into a fermionic representation of spins, you're endowed with some additional internal symmetries, which are not present in spin space. Okay. And the thing is that since these two symmetries don't commute, you can sandwich a rotation by a particle hole. So you have a particle hole transformation and you sandwich it on both sides by a U1 rotation, right? And the thing is that this is an SU2 matrix. So you can do a local SU2 gauge transformation. You can perform it on every site on a lattice, which keeps every component of the spin operator invariant independently, okay? And since any physical Hamiltonian only involves the spin operators, not the fermions, right? This symmetry acts internally within the spin. So besides the global SU2 spin rotation symmetry from SI.Sj, so preserving the dot product, there's an internal symmetry that arises in this fermionic representation. And it is this local SU2 gauge transformation, which is the whole crux of this classifying spin liquids, because you're given, it is so spin liquids which all look the same when you applied physical space-time symmetries. Now will not look the same when you supplement the space group by these gauge symmetries, because different spin liquids will transform But then you can undo that change by applying different gauge transformations. And you'll be able to use these different gauge transformations to tell which spin liquids are different. Okay. So this gauge structure was discovered in the paper by Bhaskaran and Anderson in '88. Okay. And this is this SU2 gauge structure. So the whole point is this additional gauge redundancy in spin-on space means that there is some freedom, right? And how physical or spin symmetries will act in this space. So when these symmetries acted in original spin space, they couldn't act, they acted linearly. But when they act in the spin-on space, which is 4-dimensional, they act projectively, which simply just means that when you do a lattice point group operation, say some 90-degree rotation on a square lattice, or a time reversal, or a spin rotation, or you do some reflection or whatever inversion, when they act on fermions, they will act up to a phase factor. And the origin of the phase factor is simply the fact that if I take a spin liquid wave function and I act by a certain symmetry, the wave function will transform. But then I will allow it to transform because I have the power of an additional symmetry which can undo that change. The whole point is that the combination of lattice symmetry plus a projection symmetry must keep the whole thing unchanged. Okay. So you're allowed to change something by say a translation or by a rotation, but only in such a manner that there must exist an SU2 gauge transformation which can undo that change. Okay. So you say that a symmetry transformation, say X or time reversal team, may be accompanied by an SU2 gauge transformation. And in mathematical terms, all you say is that the symmetry is represented projectively in the spin-on Hilbert space, and linearly otherwise. So the thing is that you can do time reversal and everything can act projectively. But the point is that you can. Very recently, it was realized that actually even spin rotations can be realized projectively. So you don't need to make the system invariant under SU2. You can allow it to change as long as there exists a gauge transformation which can undo it. And this gives rise to the whole business of Majorana spin liquids, which Hermeli and others have been, Chris Lauman and
just a simple, very clarification question. So normally a projective representation has only a phase factor, but you are saying it's not only a phase, now it's an SU2 basically, which is a gauge.
Yeah, very good. So the thing is that if you solve the commutation relations imposing a phase factor, you get what I call as U1 spin liquids. If you do it with a full matrix, you get SU2 spin liquids. If you have plus minus identity, you get Z2 spin liquids, which have deconfined, spin-ons, which are not, spin-ons are free in that case. So the thing is that, and when you do a linear implementation of spin rotation, you get symmetric spin liquids, which are the conventional ones that sort of I've been studying. So the thing is that the whole business of classifying spin liquids is actually going into this fermionic space, having this additional gauge structure, and allowing your wave functions to change as long as there exists a gauge transformation, and then using these different gauge transformations will actually undo that change to say which spin liquids are different. Okay, this is the whole thing. Okay. So recently with my PhD student, we had this paper and we classified this PhDs on, say all 3D cubic systems, simple cubic, body-centered, face-centered. And of course, this is now a standard method in our field to, how to classify spin liquids.
So again, Yasir, so let me bring back the issue again. So it looks like if we want to have discussions, we have to really rush through the rest, and you have also this QAD tree and all this. So I would just ask you to think about a right place to stop so that we can have some discussions maybe. And
so I think this is a good place to stop. I think one slide, and I think it should be good. One slide, and then that will be a natural point. So the goal of the PhD framework is to actually classify quadratic spin Hamiltonians. Okay. So the point is that when you have spins and you write it in terms of fermions, you will, if you are paying enough attention, you'll realize that actually you get 4 fermion interaction terms. But then they can be decoupled by Habat-Shutanovich, and you basically land up with some quadratic theory, which are just free fermions, So psi I dagger, psi j, with some, transition elements, matrix elements, right? And so these simply just consist of, this is what is called as a spin liquid ansatz. So you can expand these things in a Pauli basis, and you land up with some hopping amplitudes and some pairing amplitudes, right? So C dagger C and C dagger terms, right? And when you specify all these link matrices on a given lattice, that completely gives you a spin liquid ansatz. Okay. And the whole job of a PhD framework is to classify how many different types of quadratic spin Hamiltonians, how many types of matrices you can have, given certain symmetry. So given the lattice symmetry, the point group, and in the gauge group. So somebody says, no, classify for me all Z2 spin liquids on a square lattice. Okay, I'll do that. So that gives you 272 spin liquids. Okay.
Sorry, I couldn't follow this at all. Sorry, I probably
So
now.
all I'm saying is that
So
write
you have this.
You have a doublet, right? You have a fermion doublet. You can write a quadratic theory, okay, which just consists of hopping terms and pairing amplitudes, right?
Right, but originally you started from the electron, which was supposed to be fragmented. But
Yeah,
now you
then I had
again
spins.
have, so yeah,
Yeah,
so this
all
psi
I'm
is the
saying-
electron or
no,
one
it's just
of
a spin. It's a spin. It's a spin.
Is just a spin. I see.
That's
Okay.
all. I will talk only about spin fractionalization now. Okay.
Okay.
So you can fractionalize a spin, and then you can write basically a quadratic theory, which this is just a spin doublet. So it's Fi up, Fi down, dagger, transpose, and you can write down a quadratic Hamiltonian. And the whole aim is to classify what are the possible spin liquid ansatz at the mean field level, right? And this just consists of hopping terms and pairing terms. So it's conveniently written in matrix form, where you have the diagonal elements being the hoppings and the off diagonal elements being the pairings. And once you specify all these link variables, you can either
Sorry,
do.
I am again very much lost. So if what is this thing that what is this mean field answers? Why you call it a mean field answer? Simply it's a expectation value of some psi.
Yeah, Uij is the expectation value of C dagger C and C dagger C dagger, or let's say F dagger in my language. Okay, so these are pairing terms. Fi, at some time Fi up, Fj down, dagger, F dagger.
No, I just have a very stupid and basic question. So you give a Hamiltonian Uij, and so now so the Uij is something is whatever you can choose. So what is it that how you determine? What do you mean by determining?
Yeah, so how you determine is the goal of the PSG. So the thing is that the PSG gives you certain constraint relations between physical symmetries and gauge symmetries, right? So so like you write translation, right? Tx ty equals to ty tx, right? Now these are all realized projectively, so up to some phase factor. So to every physical symmetry, you will associate a gauge transformation. So let's call it GTX, GTY. Then
so you are classifying gauge symmetries of the Hamiltonian H0. What possible kind of what?
You're satisfying.
What kind of projective representations of the gauge group or whatever of some symmetry?
Yeah. So whenever you have a translation symmetry, let's say translating in the x direction, you have a corresponding gauge transformation GTX, right? So you would solve the whole group algebra. So GTX TX, GTY TY, GTX inverse, TX inverse, GTY inverse, TY inverse equal to e to the power I some theta sigma 3. Okay. So you will write down the whole group algebra. That is the commutation relations between all point group operations, including time reversal, which of course commutes with everything else. And then you will solve this, and you will get all these SU2G matrices corresponding to a certain point group or time reversal symmetry. Once you're done with that, you can then solve consistency relations between these gauge elements and these, these ansatz. So the Uij, that is the link variables on a lattice. And you can extract, you can have, let's say, different PSGs will then give you different UIJs, different ansatz.
So you mean a class of UIJs? It's not a unique solution for such. You mean
a class of UIJs. Yes. So like in a square lattice, you will get 196 of them. On a Kagome, you'll get 20, triangular, you'll get 20, honeycomb 160.
Yasir, if I may interrupt, the purpose of this H0 is to do this classification. But if you go back to the original spin Hamiltonian, I think I'm getting a little confused. You'd end up with a quartic Hamiltonian in
precisely. Yes. So you'll end up with a quartic Hamiltonian. So what you do is that when you get F dagger F, you get a quartic term, you do a mean field decoupling.
Okay.
That is, you decouple in the F dagger F channel and the F dagger channel.
Okay.
And you land up with a non-interacting theory, which is, of course, this describes free fermions, right? It's just hopping and pairing and moving in a background some magnetic flux. That's all.
Right.
But the point is, this is, of course, a wrong picture. So the mean field here is completely absurd. Okay. But the hope is you can recover back the original Hilbert space either by projecting out all these doubly occupied and empty sites of the fermionic representation, because the Hilbert space of the original spin model is either spin up at a site or spin down. It's two-dimensional.
Right.
But here in the fermionic, you have empty sites and you have doubly occupied sites. So what you'll do is you have to project it out. So that is the job of this projection operator. And fortunately, you can actually do it exactly by Monte Carlo sampling. You can go configuration by configuration, construct a Markov chain. Every time you throw a move, you don't accept configurations. You don't throw actually proposed configurations which are empty or which are doubly occupied, and you can recover back And this actually amounts to incorporating gauge fluctuations back into the picture. Because what we did was that we cut the spin operator into two halves, right, into fermions. And we got a quadratic theory, which is of course wrong, because the original model is actually strongly interacting.
Right.
It's a 4-fermion interaction. So you must incorporate back fluctuations beyond mean field. And the simplest fluctuations you do either in a low energy effective theory are phase fluctuations or amplitude fluctuations of these fields. And or you can actually do a numerically exact incorporation of these fluctuations of the temporal component of the gauge field, that is this lambda, which is just the Lagrange multiplier, which enforces the 1 fermion per site constraint. Because the moment you go into a fermionic representation, you must be careful. You've changed the Hilbert space, right, in the mean field. So in order to go back, you must have a Lagrange multiplier term which enforces the 1 fermion per site constraint.
Right.
In a low energy effective theory, you only do it, let's say, on an average, but numerically you can do it exactly in a Monte Carlo sampling, right? So you sample only over those configurations which satisfy this,
Right.
And that basically amounts to the fact that this lambda is the temporal component of the gauge field, and these uij e to the power I theta ij are the fluctuations of the spatial component of the gauge field. The lattice part is the uijs are the lattice part, and the lambdas are the on-site terms, which are the temporal component of a U1 gauge theory. And you can actually, let's say, exactly take into account the temporal fluctuations and completely, integrate them out. And what you land up with is then a bona fide wave function, a wave function which lives in the correct Hilbert space after you've projected. And then you can do numerics with this wave function. You calculate energies, you can calculate correlation functions. Of course, it's still a variational state. I mean, if I could exactly incorporate also temporal fluctuations of the spatial part, I would have solved the many body problem exactly. It's not possible. And you can either do a low energy gauge theory, effective theory, right? So yeah, I mean, and then, this mean field ansatz then has a special property in a sense, the subset of gauge transformations which keep it absolutely invariant, right? It's called the invariant gauge group. So when I act by a SU2 matrix on the left-hand side, like Wi, Uij, Wj dagger equals to Uij. So the subset of transformations out of this PSG, right, that I have, which keeps this ansatz absolutely, invariant, is called the invariant gauge group. The power of that is like in the Landau's theory of symmetry groups, that determines the nature of low energy excitations. So when this is a Z2 symmetry, when it's a U1, SU2, will tell you whether, you have 3 gapless gauge bosons, you have one of them, or the theory is, gapped, it's a Z2 spin liquid. It characterizes the emergent low energy gauge fluctuations. So it's not
in the language of low energy theory, it is like you have some Coulomb branch of the gauge theory where a subgroup is unbroken, but okay, so it is.
There's a subgroup which is unbroken, which is basically a low energy property. It's a property of the ground state, but that also determines the nature of the fluctuations beyond. So the PSG is nothing but the ordinary symmetry group supplemented with these gauge transformations corresponding to every lattice operation. And it's therefore, it is these G matrices which enable you to distinguish spin liquids with the same space group symmetry. So in physical space-time symmetries, all spin liquids have the same. They don't break any symmetries, okay? But it is actually these G matrices. And that is the whole, let's say, the whole idea behind PSGs. It's a way to distinguish phases that have the same physical symmetries. Okay, so I think I will stop here. I've already gone way beyond. I mean, my God, I mean, I was very slow. I'm so sorry about that.
No, it is perfect. I think you covered a lot of topics.
And we were also interrupting you.
Yeah.
No, but I thought that it's better that I carry everyone along rather than just flash something.
No, absolutely. That's the whole purpose. So we should probably schedule it either maybe in the first week of January. Maybe you can start with you because we have to find speakers. We can.
Or if you want to do it early, you can also do it. That will relieve some stress of my.
Okay, whenever is your
whenever everyone wants. I mean, the participants are left are the most interested, so they decided it's limited numbers of 15, right?
Yeah, so maybe we can continue on next week, Monday, if it's okay for everybody who is here. Maybe these are the people who will join back most likely.
No, so I'm not around next week, Monday.
Okay.
So when are you there, Raj?
After 30th, I'm back.
Oh, your 30th, you're back. Okay, then we can do it in January. It's fine. I mean, from my side, it's fine.
Okay, but we can have discussion off the record. But let me just finish with maybe some discussion and questions now. So Yasir,
just
so maybe we should ask some questions to Yasir and try to if there are some short questions. Yeah.
Ian, can I ask?
Sure, definitely.
Yasir, this is this fractionalization going to fermion operators is very similar to, sort of reminiscent of going from a Lie algebra to a graded Lie algebra, because it's like this f is like the square root, so to speak, of the spin operator.
Right.
Is this?
I don't know actually. Graded. You'll have to teach me these graded Lie algebra. The only connection I could make with this projective representation, and please correct me if I'm wrong, is to do in the Galilean group, right? You have a 9-parameter thing, and then you formally add an identity element which commutes with everything else.
Yeah.
And
that's
then you have
a central extension. That's
central extension which adds mass.
Which adds mass, which is a free pair. It's just a structure constant, right? Mass just appears as a structure constant in the commutation relation between P and the boost, right? The generator.
No, but for these kind of things, you can show this central charge is equivalent to a U1 projective representation. It simply adds.
No, but the idea of adding that whole extra thing is to basically go from projective to linear representations, right?
Yeah. But you could think of it also as a okay. Then let me explain. So there are certain projective representation where you can always remove the phase term by redefining the Lie algebra, right?
Yes.
You can always take the Lie algebra elements and add some constant to it.
Yeah.
And then it will remove the remove this extra phase.
Yeah.
If you have a central charge, then it's not possible to remove this central charge by redefining the Lie algebra elements.
Yeah.
Right?
Yeah.
And this is, but in this case, but still it's a U1 projective algebra in your language, because it simply amounts a U1 phase. Yeah, but what you are saying, you're going much beyond the traditional thing that is discussed in literature. It is.
Yeah, originally it was the U1, but then Bhaskar and these guys discovered that it's actually the symmetry is SU2. Affleck discovered U1, and then it was realized that it's actually much larger than that. It's SU2 here. In fact, if I'd fractionalize not in terms of fermions, but in terms of bosons, then I would land up with a U1. That's the largest group you can have. Okay. So in bosonic fractionalization schemes, which are also widely employed when you want to study, condensation of bosons and going into magnetic ordered states, that kind of transitions, people use bosonic fractionalization schemes. Yeah. In fact, they were studied earlier than fermionic ones, but for technical reasons, now fermions are proving better because there you cannot describe gapless spin liquids, for example. So I mean, when I move along next time, I'll go on to spin-ons in 1D. I mean, I'll explain to you, the fractionalization in 1D, the experimental signatures that have been seen of spin-ons in 1D, where the magnon, which is like, when you do a spin flip from -half to +half, fractionalizes, and it's that relation with the, matching with the Bethe-Ansatz solution. Then comes the most, let's say, the interesting part about the U1 Dirac spin liquid, which is essentially the mother, and some very recent results obtained in 2020 regarding the scaling dimensions of monopole operators. So, so the low energy theory of this, of this Dirac spin liquid is basically QED3. You have four flavors of, fermions, basically, and you have to, so you basically have, so the tricky question is that what happens?
Yasir, you are going to continue this anyway.
Yeah, I will continue. I mean, I will discuss this.
So I think we should conclude very soon now. Actually,
yeah.
I have a question about what you have discussed so far. It's actually a very trivial mathematical question.
Yeah.
It's not maybe relevant so much for actual condensed matter. But suppose you have S3, your space is your S3 and you discretize this. Then you are saying that essentially this Uij are like Aijs, the gauge fields, right? And the point is that you could think that you have an SU2 gauge transformation of some. So you're saying that if you apply something like a point group or whatever, you will essentially also generate a gauge transformation. But the point is that if you take a gauge transformation globally, not all gauge transformations can be smoothly deformed to the identity everywhere. You can do it locally always, but not everywhere. For example, for example, in the case of S3, right? And if you have SU2, there can be a lot of inequivalent gauge transformations, which are topological inequivalent, because not all of them can be smoothly deformed to identity everywhere. Okay. So in this case, is there some reflection of this in this story?
So gauge transformation is so smoothly connected to the identity.
Yeah, there are many examples of that, right? There are many.
Yeah. Well, in this case, so in some sense, if I understand you correctly, so what happens is that when you classify all these PSGs, right, without the ansatz, you just classify algebraic PSGs, so the set of inequivalent G matrices that can be realized on a lattice. Then when you go about finding the ansatz or the quadratic theory that realizes that PSG, if you restrict your links to certain neighbors or something, then many of these PSGs collapse onto each other. Okay, so it's that you might require to go to certain length in the link variables to be able to distinguish different PSGs given a certain mean field ansatz.
Sorry,
But
what do you mean by they collapse onto each other? I didn't get it.
The collapse onto each other is that you cannot physically distinguish them at the ansatz level because they might distinguish themselves. The difference might distinguish themselves. So the G matrices, when you calculate the U's, right, the physical wave functions, right, these physical wave functions, for different PSGs would be different. But then these are link variables, right? So you start from a point and you define nearest neighbors, second neighbors, third neighbors, fourth neighbor. It could be that up to fourth neighbor, both ansatz look the same, right? They collapse onto the same. But at fifth neighbor, there's a different sign structure, right, which enables you to distinguish. So I don't know. I mean, in this restricted sense, if you're talking about certain, different PSG classes collapsing onto each other in that sense, I mean, if I understood you.
No, I'm not talking in the operational sense that like the way that you are talking about. So you're talking more of an operational picture. But suppose if I want to mathematically distinguish different PSG, should I also take into account this global versus local? The fact that there are a lot of global gauge, there are a lot of gauge transformations which are not globally equivalent to each other.
Are you saying SU2 has this feature?
SU2 has this feature on S3.
Because it's,
in SU2.
The manifold is S3, which is simply connected. So I don't see how you could possibly.
Yeah, because if you take so SU2 is actually S3 also.
Yes.
And the homotopy group of S3 to S3 is essentially a Z.
Right.
So therefore, you can have many inequivalent maps from SU2 to S3, which cannot be smoothly.
Okay. So
okay. But I think we should discuss this. I mean,
okay, good.
Understand this. Yeah.
So let us take maybe one or two more questions, if there are any, and conclude for the moment, and we will return in the. Okay, it seems like people are really, it's too late. So, okay, let us thank Yasir for this beautiful, beautiful talk. And it was we learned a lot from you.
Thanks, Yasir. Ayan, just one quick question. So these talks are the recordings available to listen to later on as well?
Yes. You could, they will be put on our YouTube channel.
Okay. I missed a part of it, so I just would like to just.
Oh my God, this is what is creating trepidation for me when Ayan said he'll put it on public domain. I said, if I say some nonsense,
Okay.
Don't worry. Nobody will find you except. Okay, great. Thanks, Yasir, and Happy New Year. And Merry Christmas to all of you.
Yeah. Wish you a Merry Christmas and enjoyable holiday season, and Happy New Year in advance. I mean, have a great time.
Same to you. Same to all of you. Bye.
Okay.
Bye, everybody.
Bye.
Okay. Bye-bye. Thanks.